All right, go ahead and write that down. Put your pencil down when you're done with that slide. You're going to hear me use the term particle. I don't usually say projectile, I say particle in motion. Same thing. Yeah. Okay. All right. So what we're talking about is we're not going to have any air resistance. We're just going to be throwing things in like outer space, but without the but still with the effect of gravity. Like it's kind of like you're here on Earth, but you take away all the air resistance. That's how we're going to be studying it. So that's the case that's assumed in all these examples and questions and problems. It's a simplification, neglecting friction. All right. Gonna write that guy down. Now I want to do a little demonstration for this one. I'm going to need somebody to sit there. best place to see it. You guys done writing? Let's keep writing. When you're done, I'll... Yeah, I think this is the best spot for it. This out. Take them off here. Got a simple job. Okay, what you're going to do on the count of 3, so when I actually say, right when I say 3, you're just going to push this off to the left like that. And then at the exact same time, I'm going to flip this. I want to flip this marker, and notice something about the times when they fall. They should land almost exactly at the same time, even though this is going to land a lot further away. So, on the count of 3. 1, 2, 3. See that? Maybe you made one sound. Did you hear 2 separate sounds? Nope, one sound. So, how is it that this falling a short distance hits the ground at the same time that that's traveling obviously much longer distance? How is that possible? It is. That's true. But how does it know, okay, I need to hit the ground at the same time this guy over here does? So that's true. Yes. Because since these equations have the equations of velocity here we go. Since this velocity, why am I writing y? Actually, you guys need to remind me, because I'm recording this over here, to write on this thing, even if it's sloppier and not as convenient. It has the added advantage of recording these PowerPoint slides where someone can watch them later. Kayla was supposed to... Oh, I'm not going to put you on blast, Kayla. So, let's go here. Let me scroll down. How's it going? Bad timing. Yeah, it doesn't. The only way that I can use it is with this. The little pad thing doesn't work. Now, I think it's a driver issue because it works as it's booting, but when Insight, whatever the heck it is, Insight 360 launches, then this doesn't work anymore.
Okay. When you let me have it.
I'm right in the middle of the lecture right now.
Do you want to drop it off like I just
Do you have a...
And I can hit it first thing in the morning and maybe get borrow one from the library? To get you through the day?
Let's see. I wish I'd have brought this pad. I have one of these kind of pads. Not exactly this Mobi 360 thing, but it's just a writing pad. If I'd have brought that, because I record these lectures and put them up.
Okay. This is Brian. He's another one of the other guys. He's working with me this week. He's a technician.
What happened?
There's a thing where that locks the mouse. So you put the function.
Well, that was easy.
Yeah. All right. There you go.
All right. Okay.
All right.
Uh-huh. Who would have known? All right. Oh, the mouse was locked. Huh? I didn't know that you could lock it. So, all right. So back to... Okay, so velocity is a vector, yes? Okay. So you have some x component and some y component, and this is going in the x-hat direction, and this is going in the y-hat direction. Now these two guys are independent of each other. Can I increase this without affecting this? Yes. Now it will affect this, this velocity vector here is dependent on both of these guys. But this component x has nothing to do with y. Do you see that they're independent of each other? I can change this guy, the thing that I'm underlining here, without affecting this. Now, I'm not saying, this is not what let me not mangle this. What I am not saying is that changing this does not affect this guy over here. I'm not saying that. I'm just saying that changing this does not affect this necessarily. Doesn't affect it at all, actually. Does that make sense? Everybody believe that? Okay. So then, when I drop this object, the fact that it has an x component, a vx, oops. These are always going to be a little funky here. Let's draw this. Has nothing to do with the fact that I'm the acceleration in the y direction. Do you guys see that? They don't affect each other because they're 90 degrees. Now, if this wasn't a right triangle here, let me go back to my marker. If this wasn't a right triangle here, that wouldn't be true. Do you guys see that? Because if I increase my y, and it's kind of leaning over here a little bit, then my x is going to increase too. But because they're perpendicular, they don't affect each other. That's the nice thing. There's a fancy math word. They're orthogonal, or you could say they're independent. They don't affect one another. This means the same thing. Okay. So what does that allow us to do with our equations of motion? Not change them. Super important. Yeah, we can rearrange them, but there's something deeper than that. I want to see if you guys can figure it out on your own. Since these are independent, what does this allow us to do with our equations of motion? Yes. Who said that? I'm gonna give you free seminar points just for that. It's so awesome. I'll give you 10 just for saying that. Okay. All right. So, yes, you can separate them. You can treat them as if they don't matter to one another. You can isolate them. You can treat them separately. You can do separate math on them and forget the other one exists for a time being. So what you saw that over here in my demonstration. You saw that both markers didn't care as far as hitting the ground is concerned. You're only worried about the y component. It doesn't matter what x component has, right? It just so happens that this one has an x component, but does this one have an x component velocity? No, it's 0. Okay? So super important. That's key. If you get that, this actually will be pretty easy for you. It's not that much more complicated than the last chapter. But do you guys see why vectors are going to be important here, and being able to componentize the vectors, breaking them up into the components? Yeah. If you're given a velocity and you're given an angle, you need to be able to, the fancy term is called resolve the vectors into components. I said componentize, this is probably not even a real word, but resolve the vectors into components, that's what a mathematician would say. Okay? So if you still are having trouble with the vectors, you can't go on. You can't do this chapter, and you'll do really bad on the test if you don't go back and figure that out somehow. Either spend some time doing some practice problems, go to Khan Academy, look up physics. They got like your guys' level physics in there. Go up and look up vectors and spend some time looking at that. Here, I can even let me bring that up here. If you didn't like my explanation, I did post it on the Haiku site. My explanation. I think I did a decent job explaining it. You can go back and rewatch what I did. But if the light bulb doesn't come on with me, it won't hurt my feelings if you go somewhere else to get the information. So let me give you an example. So you come over here. Khan Academy. So am I clear, guys, that you can't do this next section without understanding vectors and being able to resolve vectors? You cannot. It's not possible because you're going to be given problems that have that are in like polar coordinates where you got a magnitude of the vector and an angle, and you've got to break that down to x and y to be able to solve this. So that's what I'm saying. I'm warning you. I'm saying you need to know the last section before you can move on. And I probably will never emphasize something like this as much as I'm emphasizing this now. Let's go to subjects. Go to Khan Academy. Go to subjects. Yeah, here it is. Science. Physics. Two-dimensional. Visualizing vectors. That's what he's going to be dealing with here.
All the problems we've been dealing with so far have essentially been happening in one dimension. You can go forward or back.
So there's that resource.
Or right or left, or you could go.
Now we've already covered this material, and some of you guys have it already. But I know that out there in the audience, there's some of you guys that don't have it at all, and I'm just saying you need to go back and cover this material until it's solid. And it shouldn't take that long. Playing with it maybe for an hour or two at home should result in a light bulb coming on. Just don't give up, okay? Quitters, yeah, don't get very far in physics. All right. So I just wanted to make that point. We might not finish this lecture this period. We might have to finish this up tomorrow. But let's keep going.
Projectile motion describes the motion of objects that are in free fall but have an initial horizontal velocity. Both balls are released at the same time and fall with the same downward acceleration. The initial horizontal velocity of the yellow ball does not affect its vertical displacement. As the ball leaves the pitcher's hand, it has a constant horizontal velocity. The force of gravity acts on the ball and accelerates it downward, causing its vertical velocity to increase. The two motions cause the ball to move in a curved path, known as a parabola. Air resistance changes the path of a projectile. When traveling through Earth's atmosphere, the projectile's path is not a parabola.
Alrighty. Go ahead and write these bad boys down. Yes, because then your assumptions kind of go out the window. Go ahead and write this down, and I'll try to make my point up here. To answer your question, velocity squared can't be a vector, right? Acceleration can be a vector, but you'd have to you can't separate it like you could before. When there's no friction, this is the acceleration in the x direction. Is there any acceleration in the x direction when there's no friction? No, because there's nothing pushing. The only acceleration that's going on is in the y direction because of gravity, right? But that guy could be a vector, okay? If you're talking about the x component, this doesn't actually work because there's no way you can break this up into vectors to separate the x and the y component separately because it's squared. Because if you put a vector here, because you can't put a vector here because v squared is a function of x and y together. Does that make sense? And multiplying these guys together gets rid of the vectors. Remember we talked about, I think we mentioned this class, we talked about dot product, like basically multiplying two vectors together. When you use this dot product here, it's no longer a vector, it's a scalar. It has no direction information anymore. And since it doesn't have direction information anymore, you can't break it up into x and y, so they're dependent on each other. There's no way to get out of that mess. The only way that you can actually do this problem is numerically. In other words, you treat them in tiny little steps. You have to treat, let it go for 100th of a second, and then recalculate the force, and then just keep adding it together using a computer program. Or back in the old days, we actually had people tabulating this stuff, like make a calculation with their slide rule, write down the value, do it again, and just break up the time steps in little chunks. That's called numeric. It's a numeric integration. So that's why it's hard. There's no there's no nice answer to it, a clean solution. And as a matter of fact, these constants here, that has to do with the shape of the nose cone of the projectile. That has to do with the density of the air. And that's the area, how big the nose cone is that's traveling through, and that's just 1/2. And so these factors actually change at different speeds. This constant is also a function of velocity, which the velocity has x and y components. So this c is not really constant over the whole range, especially when you talk about gun bullets. There's a function that goes in here called g, and it's just data that's been collected by firing bullets down a range. And then the coefficient of drag for the bullet is just basically information compared to how your bullet compares to this constant g. And that's called the drag coefficient. And from that you can calculate how the bullet flies, but you have to do it numerically. You have to do it in a computer program. There's no solution. Hopefully that answers your question. Way more complicated, yeah. These are nice, easy solutions, yeah. Area, the cross-sectional area of the projectile. Yeah, I wrote a calculator program to calculate, like with my gun, how much the bullet drops downrange. And so I get the manufacturer, the ballistic coefficient for the manufacturer, and I could get the muzzle velocity for that round, or if I really wanted to be careful, I could actually measure it. You measure it a meter out from your barrel. You put a little detector that detects how fast it goes. And then if the density of air depends on what altitude you're at. If you're higher elevation, like in the mountains, this is lower. If you're lower down, this becomes bigger. If the air is more humid, if it's hot, rho goes down. If it's cold and dry, rho goes up. So I can plug all those factors in, what altitude, and it'll tell me what the drop is for the bullet. It'll tell me how many inches. So if I'm going to hit a target at 100 or 200 yards, 300 yards, 405, all the way out to thousands of yards, it tells me how much I need to raise my gun up for that bullet to land on the target. And it can count like minutes of arc, so I can adjust on the scope, because the scope's marked off in like quarter or 8 minutes of arc. So it took me a lot of hours to do it, but so I have intimate acquaintance with that problem. I did it for fun. I did it at Bloomington High School the first year I taught physics, just to see if I could do it. And it was a lot of work. Go ahead and write these guys down. And that science is called exterior ballistics. All right, guys. It's been fun. We'll finish this up tomorrow.